everybody. Thank you for coming to How to Make a Basic Artificial Neural Network. So I have simplified this, so the only prerequisite for understanding this is 3rd grade math. So if you can do multiplication and division or plug things into a calculator, it should be totally fine. And first of all, what is a neural network? We're going to talk first of all about sort of a natural neural network that's inside of our brains. You've probably seen pictures like this before, and you may also know that the large bulby structures are called neurons or nodes, and then the sort of pathways that go in between those are called the synapses. So in the process of growing up, when you're a baby and a child, all of these structures are forming. Sorry, our Wi-Fi is not very great. Okay, so what happens is, as we are perceiving things, like we see something, we smell something, we touch something, those are kind of inputs into your brain. And then those travel along these kind of neurons that are able to sort of what we call thinking and remembering things. And then they can make decisions. And when the structures become kind of more dense and more thick in between the nodes, that's how it's learning to slam on the brakes when you see a red light. So some of these pathways become very, very fast, the ones that are really critical for our survival. When you're an adult, the structure kind of is already in place, but of course you still do learn memories. So, next one. So that is your brain. And we are going to go like this. This is your brain on drugs. You guys probably remember those 80s commercials with the frying pan. This is actually not your brain on drugs. This is just what it looks like as your brain is thinking and sending these signals through all the neurons and the synapses. It's pretty cool. Just kidding. So what's an artificial neural network? So it's a much simpler system actually, but it follows some of those same rules and structures as your brain, as your neural network. And it is a system that can learn patterns from data. So we can feed it in like images or text, characters, sounds. Probably someone's working on one for smell, I'm not sure. And so for example, some inputs that we are using for our spam classifier would be things like, for a photo on House, the title, the username, an email, and then an output would be spam or okay. So we're going to feed in thousands of these examples like this that are labeled with whether they are spam or not. For example, we have like muscles galore, and the user is Maxim76, and this is his email. And we're going to give all of this into the neural network, and it will be labeled. And then it should be able to learn these patterns, and we could give it something it's never seen before, like this one, kitchen sink, Mac Johnson, MG, and it should be able to tell us, give us this output. So it's learning all of those patterns. So some examples of possible applications for an artificial neural network are classification tasks, things like visual match, which right now is our only current application of a neural network at House. Also categorizing spam, like we talked about, product categories, facet values, image quality, things like does it have watermarks or is it dark or blurry. So currently these are not using neural networks, but we would like to try and experiment and see if we can get better accuracy using that. And then prediction. So the other task that neural networks are good at is prediction. So this would be looking at something like, given the frequency and the location of an ad, predict how many clicks we're gonna get. So then we could decide like how much should we spend on the ads based on how much we think we're gonna get out of it. That's good for biddings. And then translations. So artificial neural networks are getting really good now at learning language models. Because you know, like in French or Spanish, other languages often have different ordering of the words. So when you're translating, you can't translate word for word. You have to actually learn and predict what order things are going to go in based on patterns and probabilities that it can figure out. Also some other things like our estimated time in traffic, our self-driving cars need to be able to predict if another car is going to swerve and hit you or not and react appropriately. Let's see. So let's build this. So this is just kind of a visualization of how this would look. You have first of all your inputs. So it's like this example we're going to go through is mathematical. It's using numbers and finding patterns in numbers. I can show you our training data that we have. So these would be inputs. Would be this first example here. We're going to tell it when it sees 1, 1, the output we want is 0. This layer in here is the hidden layer. The reason it's called hidden is that it doesn't show up in the output. It's just an internal kind of thing. But you can see these are all neurons. This is also a neuron. These are just the inputs. In between we have what's called the synapses. And we will put weights on how important things are. So a simple way of looking at it is maybe you're gonna feed the neural network a picture of a bus, and you want it to decide if that's a bus and learn a pattern, looking at lots of buses to be able to predict that. So you could have sort of some functions that are in this hidden layer. That might be one that's detecting like what size it is. Another one might be detect like does it have wheels or not. Also like what shape? Is it like a box shape? So functions in here can be a lot of different functions. There can be ones that are just like a yes or no, like does it have wheels or not? Okay, like that can be a helpful signal. But they can also be functions that kind of can scale. We won't worry too much about that, but they can scale down the numbers so that they are appropriate. Okay, so first, the first thing that you're going to do is just assign random weights to all the synapses. We really don't know, from looking at a massive data set, you wouldn't really know which of the inputs are necessarily going to be most important for signals. So, for example, like one of the inputs was like size for the bus example. That may turn out to not be the most important thing because there may be a lot of large objects. It may be more important that it looks at this input, which would be like the wheels, right? So you may have a lot of inputs, and it needs to figure out which ones are most important, and then go put more weight on that. So that's kind of what it's learning. So going back to this, the pattern, you guys can probably see since this is a very simplified example. So it's basically, you can see if these inputs are the same, it should give a 0. So these ones that are the same are zeros. And anytime that these are different, it should give us a 1. So we want it to be able to predict if we give it something it's never seen before, that the output should be 1 on that one.
Sorry, you said that
Yeah, if you have
hidden, the hidden portion is where you put where you would put in the function.
Mm-hmm. Yeah, functions that can help us see what patterns there are to the data. Right. Okay, so we're just putting some kind of random weights, and then there's really just 4 steps that you need to follow, and it's not required that you really think about it or figure out how to do this. You really are just finding numbers, and then you're plugging them into the next equation. So it's like it's really a fairly simple mathematical problem that you guys are all capable of doing. So I mean, the first thing, you know, we're looking at these inputs, and then these are both leading into this node or this neuron. So we're just going to follow the first equation, which is like the input times the weight, and the input plus the weight, and we're just adding those. So we're finding what's called a hidden sum. And we're going to follow like very similar kind of steps here. We're going to find a hidden layer. So again, when we get to a neuron, there's always a function. So that's when we're going to apply the functions like I talked about. In this case, this is called a sigmoid function. So it's just like an S-shaped curve. If you ever study calculus and see there's kind of curves like that. When you're looking at neural network data, they usually don't follow a linear pattern. So there's not like those graphs that just go, you know, there's a line that follows all the data. These are, you know, more complicated patterns. So we're just going to plug this in. We're going to follow these steps. Yeah, so I mean, again, we're just going to now be multiplying what we got here by these weights. We'll sum those up, and then this is another neuron, so we apply one more function there. Okay, oh yeah, so you can see when we got here, the output we found is 0.77. So the prediction that we got on our first try is 0.77. You can see that that's not correct, right? We know that the answer should be 0 here. But what's cool is now we know how far off the network is. We can use that number to then go backwards and adjust the weights so that we're getting them so that they're, you know, they're weighting the inputs in the right way. So I'm just gonna go flip through this really quick, just more functions and more simple like additions and multiplication that we go backwards.